Hello, friend. Welcome back. Or perhaps, welcome for the first time. Tonight, the sky feels different, doesn't it? Darker, quieter, as if the universe itself is holding its breath, waiting to tell you something it's been keeping secret for billions of years. Out there beyond the glow of city lights, beyond the edge of what we can see with our eyes alone, the cosmos is speaking. Not in words, not in language, but in whispers we've only just begun to hear. Faint pulses of energy, brief flashes of light, signals that cross unfathomable distances just to reach us carrying messages we don't yet understand. Some last only milliseconds, others 72 seconds, and some we've only heard once. Before we drift into tonight's journey, I want to say thank you for being here. If these quiet nights of discovery bring you comfort, if you find peace in questions that have no easy answers, you might like to stay a little longer. You can gently tap the like button if this resonates with you. Subscribe if you'd like more stories whispered softly into the dark, and ring the little bell, not for noise, but so the next quiet night can find you again when you need it most. Now, let's drift. Tonight we're going to explore the most enigmatic signals ever detected from the universe. Not the ones we understand, not the ones that fit neatly into textbooks, but the ones that made scientists stop, lean forward, and whisper to themselves in the stillness of observatory control rooms at 3 a.m. The ones that changed everything, or changed nothing. We still don't know. You don't need to understand it all tonight. Just rest. Let curiosity do the listening. And remember, sometimes the most profound truths come not in answers, but in the beauty of not knowing. The universe is not silent. We just haven't learned its language yet. Think about this for a moment. Right now, as you listen to these words, radio waves are passing through your body. Waves from distant galaxies, from dying stars, from events that happened when Earth was still molten rock. They move through walls, through skin, through the very atoms that make you, well, you. Invisible, unfelt, unheard, until we built machines sensitive enough to catch them. In 1931, a young engineer named Karl Jansky was trying to solve a problem for Bell Telephone Laboratories. He wanted to identify sources of static that interfered with radio communications. He built an antenna large and ungainly that rotated on wheels from a Model T Ford. Locals called it Jansky's merry-go-round. Every day it turned, slowly scanning the sky. And every day Jansky noticed something strange, a hiss, a persistent static that rose and fell in a rhythm that matched not the Earth's rotation, but something else, something cosmic. It took him months to realize what he was hearing. The hiss came from the center of our galaxy, from a place called Sagittarius A star, though he didn't know its name then. He was hearing for the first time in human history the voice of the Milky Way itself, not metaphorically. Actually, radio waves born from the chaos of matter, spiraling into what we now know is a supermassive black hole, had traveled 26,000 years to tickle the wires of his antenna. Jansky published his findings in 1933. The New York Times ran the story, "New radio waves traced to center of the Milky Way." The universe had spoken, and we had listened. But here's the thing. Most people didn't care. It was the Depression. The world had bigger problems than cosmic static. Jansky wanted to build a bigger antenna, to listen more carefully, but Bell Labs moved him to other projects. He never pursued radio astronomy again. He died in 1950 at 44, his greatest discovery largely forgotten during his lifetime. But the universe kept whispering, and eventually we learned to listen better. Fast forward to the 1960s. The Cold War was at its peak. The United States launched a series of satellites called Vela, designed to detect gamma rays from Soviet nuclear tests in space. On July 2, 1967, Vela 3 and Vela 4 both recorded a flash of gamma radiation. But it didn't match the signature of a nuclear weapon. It was too long, too irregular, and it came from space. Deep space. Scientists kept this discovery classified for years, unsure what they had found. When they finally published in 1973, they revealed something astonishing. The universe was experiencing violent explosions so powerful they outshone entire galaxies for a few seconds. They called them gamma ray bursts, or GRBS. In a few milliseconds, a single GRB releases more energy than our sun will produce in its entire 10 billion year lifetime. We still don't fully understand them. Some come from the collision of neutron stars objects so dense a teaspoon of their material would weigh 1 billion tons on Earth. Others come from hypernovae stars so massive their deaths create black holes. For a brief moment, they are the brightest things in the universe. Then silence. Just an afterglow fading like the memory of a dream. These weren't messages, they were events. Catastrophes. Cosmic violence on a scale our minds struggle to grasp. But they taught us something crucial. The universe is far stranger, far more dynamic than we imagined. It whispers yes, but sometimes it screams. Have you ever wondered what it would be like to hear a sound that's traveled longer than human civilization has existed? What stories it might carry? What worlds it might have passed? In the decades since Jansky and those first gamma-ray detections, we've built ears all over the planet. Radio telescopes the size of football fields. Arrays of dishes scattered across deserts, all working as one. We've launched satellites that can see wavelengths our eyes never could. X-rays, ultraviolet, infrared. We've learned to translate the universe's whispers into data, into images, into understanding. But some signals refuse to be understood. Some arrive once impossibly strong and then vanish. Some repeat in patterns we can't predict. Some seem artificial structured, deliberate only to be revealed as something mundane, a reflection of our own technology. And some remain mysteries suspended between explanation and wonder. Here's what makes these signals so haunting. They exist at the boundary of knowledge. They remind us that for all our telescopes, all our equations, all our theories, the universe still has secrets. It still surprises us. It still humbles us. Scientists often talk about the wow of discovery. That moment when you see something that shouldn't exist according to everything you know. When your assumptions shatter. When you realize the universe is bigger, weirder, more mysterious than your theories allowed. These signals, the ones we're going to explore tonight, they are those moments. Frozen in data, preserved in memory, still unexplained. Some believe these signals might be messages. Deliberate transmissions from civilizations, millions of years more advanced than ours, trying to reach out across the cosmic ocean. Others think they're natural phenomena we simply don't have the physics to explain yet. New kinds of stars, new forms of matter. Events our theories can't predict, because we're still missing pieces of the puzzle. And maybe they're both. Maybe the universe itself is more alive, more communicative than we dare to imagine. The physicist Enrico Fermi once asked a simple question that haunts astronomers to this day. Where is everybody? If the universe is so vast, if there are billions of galaxies, each containing billions of stars, if even a tiny fraction of those stars have planets capable of supporting life, then where are all the aliens? Why haven't we heard from them? Why is the cosmos so quiet? This is called the Fermi paradox, and it has many possible answers. Maybe civilizations destroy themselves before they can communicate. Maybe the distances are too vast. Maybe we're looking in the wrong places or listening at the wrong frequencies. Maybe intelligence is vanishingly rare. Or maybe they're already here in these signals we can't decode, speaking a language we don't recognize, waiting for us to learn. Tonight, we won't answer that question, but we'll walk through the evidence, through the signals that made scientists lean forward in the dark and wonder if just maybe they were hearing something extraordinary, something that would change what it means to be human. Because that's what these signals do, even the ones that turn out to be natural. They expand our sense of what's possible. They remind us that we are part of something incomprehensibly vast and ancient, that our planet is a small stage in a cosmic drama billions of years old, that we are all of us made of atoms forged in the hearts of dying stars, listening to the echoes of creation itself. The universe is speaking, constantly, in radio waves and gamma rays, in gravitational ripples and particle showers, in light that left distant galaxies when dinosaurs walked the Earth. It speaks in mathematics and mystery, in patterns and chaos. And we, fragile beings on a pale blue dot, have learned to listen. Not perfectly, not completely, but we're trying. So let's begin where many of these stories begin, with a single night, a single moment, a single signal that appeared on a printout and made one astronomer write 6 letters in the margin that would echo through history. 6 letters, written in red ink, on a computer printout. That's all it took to create one of the greatest mysteries in the history of astronomy. Wow, simple, spontaneous. The kind of thing you write when you see something that shouldn't exist. When the universe hands you a riddle wrapped in radio waves. When 72 seconds change everything you thought you knew about being alone. It was August 15th, 1977, a Monday night. Most of America was watching television, eating dinner, living ordinary lives. But at the Big Ear radio telescope in Ohio, a computer was listening to the stars, silently, patiently, the way it had been listening for years. The telescope itself looked nothing like the massive dishes you might imagine. It was a flat reflector the size of 3 football fields built on the grounds of Ohio Wesleyan University's Perkins Observatory. Its official name was the Ohio State University Radio Observatory, but everyone called it Big Ear, because that's what it was, an ear, listening. And that night, it heard something impossible. Jerry Amon was a volunteer astronomer, not famous, not seeking glory, just a man who loved the stars enough to spend his evenings analyzing data printouts. The telescope worked automatically, scanning the sky, recording radio intensity at different frequencies. Every few days, the computer would print out the data, long sheets of numbers and letters representing signal strength. Mostly it was noise, random fluctuations, the background hiss of the universe. But on August 19th, when Amon reviewed the printout from 4 nights earlier, he saw something that made his breath catch. A sequence that climbed from the baseline like a mountain rising from a plain. 6, E, Q, U, J, 5. Each character represented a signal strength. The scale went from 1 to 9, then A to Z for anything stronger. U was intense. J was extraordinary. And there it was. A curve. A bell curve. Exactly what you'd expect if a powerful focus signal had swept through the telescope's field of view as Earth rotated. Amon grabbed his red pen and circled the sequence. In the margin, he wrote those 6 letters that would define his life. Wow. Because this wasn't noise. This wasn't random. This was a signal. Strong, narrow band, coming from deep space. The signal lasted exactly 72 seconds. That's how long it took for Earth's rotation to sweep the telescope's beam past the source. The frequency was 1420 megahertz. If you know anything about the search for extraterrestrial intelligence, that number should make you pause. 1420 megahertz is the emission frequency of neutral hydrogen, the most abundant element in the universe. It's a frequency astronomers call the cosmic water hole, because it's where we'd expect intelligent civilizations to broadcast if they wanted to be heard. It's quiet, protected from interference, universal, a frequency any scientifically advanced species would know. The signal was so strong it was 30 times louder than the background noise. To put that in perspective, imagine you're in a quiet library and suddenly someone starts shouting through a megaphone. That's the difference. And it came from the direction of the constellation Sagittarius, near a group of stars with no known planets, no nearby objects that could explain it. Just empty space. Or so we thought. Here's where the mystery deepens. The Big Ear telescope used two receivers called horns, separated by a few minutes of sky rotation. If a signal was real, it should appear in both horns. The WOW signal appeared in only one. The second horn, which scanned the same patch of sky just minutes later, detected nothing. Silence. As if whatever sent the signal had turned off, or moved, or stopped existing. Amon and his colleagues immediately began follow-up observations. They pointed the telescope back at that exact patch of sky. Night after night, week after week, for months, then years. Dozens of subsequent searches, different telescopes, better equipment, more sensitive receivers. And they found nothing. The signal never repeated, not once, not ever. It was as if the universe had whispered something profound and then gone forever silent. This is what haunts astronomers, not the signal itself, but the silence that followed. Because in science we trust patterns, we trust repetition. A signal that appears once and never again is impossible to study, impossible to verify, impossible to explain. It exists in that uncomfortable space between data and dream. So, what was it? That's the question that's consumed researchers for nearly 50 years. The explanations fall into three categories: human interference, natural phenomena, or something else. Something we don't want to say out loud, but can't stop thinking about. Let's start with human interference. Could the WOW signal have come from Earth? A satellite? A passing aircraft? Radio interference from someone's television or microwave? It seems unlikely. The frequency was protected reserved for astronomical observation, and the signal's behavior rising and falling in that perfect bell curve matched exactly what you'd expect from a fixed celestial source, not a moving human object. Plus, Big Ear had been operating for years. Amon and his team knew what interference looked like. This wasn't it. But here's the thing about science. We make mistakes. We miss things. In 2017, a researcher named Antonio Paris proposed a natural explanation that seemed almost too mundane to consider: comets. Specifically, two comets 266P/Christensen and 335P/Gibbs that were passing through that region of sky in 1977. Comets, Paris argued, are surrounded by clouds of hydrogen gas that could emit radio waves at 1420 megahertz. Maybe the WOW signal wasn't a message. Maybe it was just a comet, an icy rock releasing hydrogen as it warmed. The astronomy community wasn't convinced. Other researchers pointed out that comets had been observed before at that frequency, and they didn't produce signals anywhere near that strong. Plus, the WOW signal was incredibly narrow band, just 10 kilohertz wide. Natural sources are usually broadband spread across many frequencies. This signal was focused, precise, the kind of thing you'd get from a transmitter, not a cloud of gas. The comet hypothesis was interesting, but flawed. It explained some things, but not others. It was a partial answer. And in science, partial answers are often more frustrating than no answer at all. So, if it wasn't human and it wasn't a comet, what's left? The possibility that keeps us awake at night. The possibility that someone or something was trying to say hello. That for 72 seconds we were not alone. That an intelligent civilization, perhaps thousands or millions of light years away, sent a signal into the void and we happened to be listening. That we heard them. Once. And then they were gone. But why would an extraterrestrial civilization send a signal just once? That doesn't make sense, does it? If you're trying to communicate across the stars, wouldn't you broadcast continuously? Wouldn't you repeat your message over and over, knowing that anyone listening might miss it the first time? Unless they were scanning the galaxy, a lighthouse beam rotating slowly, illuminating different patches of sky. We happened to be in the beam for 72 seconds, and then it moved on. Or maybe it wasn't meant for us at all. Maybe we were eavesdropping on a conversation between two distant worlds and we caught just a fragment, one sentence in a language we don't speak. Or maybe they're gone. Maybe the signal left its source 1,000 years ago, or 10,000, or 1,000,000. Maybe the civilization that sent it rose, flourished, and fell to dust while the signal traveled through the void. Maybe we heard an echo, a ghost, the last whisper of a world that no longer exists. Do you find that thought comforting or terrifying? The idea that we might be listening to the voices of the dead, carried on waves of light and energy across impossible distances. Here's what we know for certain. The WOW signal was real. It was recorded. It exists on that printout now, carefully preserved in the archives of Ohio State University. It wasn't a mistake. It wasn't a glitch. Something happened that night. Something generated a powerful, focused radio transmission at exactly the frequency we associate with the search for intelligent life. And then it stopped. The Big Ear telescope was demolished in 1998 to make way for a golf course. Yes, you heard that right. One of the most important radio telescopes in history, the instrument that detected possibly the most significant signal ever received from space, was torn down so people could play golf. The irony is almost painful. We spend billions searching for signs of life in the universe, and when we find something extraordinary, we pave over the evidence. But the search didn't end with Big Ear. The WOW signal inspired generations of astronomers. It reminded us why we listen, why we build bigger telescopes, why we scan the skies night after night, hoping to hear something that proves we're not alone. Because that's what the signal represents even now, 47 years later. Hope, the tantalizing possibility that somewhere out there someone is speaking, and maybe they want us to answer. Since 1977, we've detected thousands of astronomical radio sources, pulsars, magnetars, quasars. We've learned to identify them, catalog them, understand them. But none of them look like the WOW signal. None of them have that perfect narrow-band 72-second signature. It remains unique, unexplained, a mystery wrapped in data. Some scientists have moved on. They've decided that without repetition, without confirmation, the WOW signal is scientifically useless, a curiosity, a historical footnote. But others can't let it go. They keep searching, keep analyzing, keep hoping that one night the signal will return, that the universe will speak again, that those 72 seconds weren't an accident or an anomaly, but the beginning of something we're only just starting to understand. And maybe that's the real lesson of the WOW signal. Not that we heard something extraordinary, but that we're willing to keep listening even when the universe goes silent. That we're curious enough, hopeful enough, stubborn enough to keep searching for answers even when the questions seem impossible. That we believe deep down that the cosmos has more to say. And we want to be there when it speaks. 72 seconds. 6 letters in red ink. One mystery that refuses to fade. The signal came from the stars, and then it vanished, leaving us with nothing but questions and that one perfect printout. Sometimes the universe gives us answers. Sometimes it gives us wonder. And sometimes it gives us just enough of both to keep us reaching for the sky. But the WOW signal wasn't the only time the universe startled us with something brief and brilliant. In fact, there's a whole class of cosmic phenomena that makes the WOW signal look almost tame by comparison. Events so violent, so energetic, so impossibly fast that when we first discovered them, we thought our instruments were broken. Flashes that last only milliseconds, but carry more power than our sun will produce in its entire lifetime. The universe doesn't always whisper. Sometimes it screams in bursts we're only beginning to understand. Imagine this. You're standing in complete darkness. Suddenly a flash, so bright it lights up the entire sky, so powerful it outshines every star in the galaxy combined. And then before you can even blink, it's gone. Milliseconds. That's all it takes. The universe just screamed at you with the energy of 1 billion suns, and by the time your brain registers what happened, it's already over. This isn't science fiction. This is real. And we're detecting these cosmic shouts almost every day now. The question is, what's screaming and why? The universe has a way of humbling us just when we think we understand it. For decades, we thought we had cataloged most of the violent events in space. Supernovae, gamma-ray bursts, quasars. We had our lists, our categories, our theories. And then buried in old data from 2001, someone found something that didn't fit. Something so brief, so energetic, so utterly strange that it took 6 years just to convince anyone it was real. A flash of radio waves, 5 milliseconds long, carrying more energy than our sun produces in an entire day, from a source 4 billion light years away. The cosmos had been shouting at us all along. We just hadn't been listening carefully enough. The man who found it was Duncan Lorimer, an astrophysicist at West Virginia University. In 2007, he was reviewing archived data from the Parkes Radio Telescope in Australia. The data was old, recorded back on July 24, 2001, but no one had analyzed it properly. Lorimer was working with a graduate student named David Narkovich, teaching him how to search for pulsars, those spinning neutron stars that sweep beams of radiation across space like cosmic lighthouses. They expected to find pulsars, routine work, textbook examples. Instead, they found something that made them question everything. There in the data was a spike, a massive burst of radio energy that lasted only 4.6 milliseconds. At first, Lorimer thought it was a mistake, equipment malfunction, interference from Earth, maybe someone's microwave. But the more he looked, the less sense that made. The signal showed something called dispersion. Radio waves of different frequencies arrived at slightly different times, with lower frequencies delayed compared to higher ones. This happens when radio waves travel through ionized gas in space. The more space they cross, the more dispersion you see. And this signal had traveled through a lot of space. Billions of light years. This wasn't local interference. This was cosmological. This was real. Lorimer published his findings. The astronomy community was skeptical. One burst, one detection could be anything. Could be nothing. But Lorimer had found something genuine. The data was solid. The dispersion was undeniable. Someone or something somewhere in the distant universe had released an enormous amount of energy in less time than it takes to snap your fingers. They called it the Lorimer burst, and it became the first confirmed fast radio burst, or FRB, a new class of astronomical phenomena, a new mystery. But here's where it gets interesting. For years after the Lorimer burst, astronomers searched for more FRBs. Some people found a few. Others found nothing. There were debates, doubts. Maybe FRBs were rare. Maybe they were errors. Maybe they didn't matter. And then, in 2016, something changed. A telescope in Puerto Rico. The massive Arecibo Observatory detected an FRB that did something no one expected. It repeated, FRB 121102, as it was cataloged, flashed again. And again, and again. Not regularly, not predictably, but it kept coming back. This was revolutionary, because if an FRB repeats, you can study it. You can point multiple telescopes at the same patch of sky and wait. You can measure it from different angles, at different wavelengths, with different instruments. And that's exactly what scientists did. They traced FRB 121102 to its source, a dwarf galaxy, 3 billion light years away, tiny, faint, unremarkable except for one thing. Somewhere in that galaxy, something was producing bursts of radio energy so intense they could be detected across a significant fraction of the observable universe. What could do that? The theories multiplied. Some suggested magnetars neutron stars with magnetic fields a quadrillion times stronger than Earth's. When these fields snap or rearrange, they could release tremendous energy. Others proposed colliding neutron stars or matter falling into black holes, or even more exotic ideas, cosmic strings. primordial black holes, events at the edge of known physics. And then there were the whispers, the uncomfortable suggestions. Could an advanced civilization generate FRBs? Could they be signals, beacons, energy transmissions for spacecraft? We can't imagine most scientists are cautious about the alien hypothesis. Not because it's impossible, but because we have a rule in science. Extraordinary claims require extraordinary evidence, and natural explanations, even strange natural explanations, are usually correct. But the truth is, we don't know. Not definitively. FRBs are still too new, too poorly understood. We're like people in the 1600s trying to explain lightning. We have theories, we have guesses, but the universe hasn't given us enough data to be sure. Since that first discovery, we've detected thousands of FRBs, literally thousands. They happen all the time, several per day scattered across the sky. Most are one-offs, brief, intense, never to be seen again, but a small percentage repeat. And those repeating FRBs are starting to teach us things. They seem to come from active star-forming regions, places where the universe is young and violent, places where massive stars are being born and dying in rapid succession. The non-repeating FRBs might come from different sources entirely. Catastrophic events, explosions, deaths, things that only happen once. There's a beautiful paradox here. The repeating FRBs and the one-time FRBs might not even be the same phenomenon. We've grouped them together because they look similar: bright, fast, radio. But that's like grouping lightning and camera flashes together just because they're both brief and bright. They might have completely different causes. The universe might be using two entirely separate mechanisms to produce what we, in our limited understanding, call fast radio bursts. In 2020, something extraordinary happened. For the first time, astronomers detected an FRB from within our own galaxy, FRB 202000428, later designated FRB 202000428A, came from a magnetar called SGR 1935 plus 2154, only about 30,000 light-years from Earth. In cosmic terms, that's next door. And because it was so close, we could study it in detail. Multiple telescopes caught it. Space-based observatories, ground-based dishes. For the first time, we saw an FRB in context, and it confirmed what many suspected. At least some FRBs come from magnetars, from those impossibly strong magnetic fields twisting and snapping and releasing energy in bursts. But that doesn't explain all FRBs. It can't. Because some FRBs are far too energetic to come from magnetars alone. Some show characteristics that don't match. Some come from environments where magnetars shouldn't exist. So, we're back to mysteries. Multiple mysteries. An entire zoo of phenomena, all producing similar-looking signals for different reasons. Do you ever wonder what it must feel like to discover something like this? To be the first person to realize the universe is doing something no one predicted. Here's what keeps astronomers awake: the energy involved. Let's put it in perspective. A typical FRB releases about as much energy in a few milliseconds as the sun releases in 3 days. That's mind-boggling. But some FRBs are even more extreme. FRB 12110-2. That repeater we talked about has produced bursts with energies equivalent to what the sun puts out in 80 years, in 5 milliseconds. 80 years of solar output. Compressed into the time it takes a hummingbird to beat its wings once. If you could somehow convert that energy into a physical force, it would be like setting off 1 billion nuclear bombs simultaneously. And that's just one burst, from one source, happening repeatedly. Now scale that up. Thousands of FRBs, happening constantly, all across the universe. The sheer amount of energy being released is staggering. And we're only detecting the ones pointed roughly in our direction. How many more are there flashing in directions we'll never see? How much of the universe's energy budget is being spent on these cosmic shouts? Scientists estimate that an FRB might occur somewhere in the observable universe roughly once every second. Think about that. Every second as you breathe, as you listen to these words somewhere, billions of light years away, something is releasing a burst of energy powerful enough to be detected across the width of the universe. The cosmos is far more active, far more violent, far more energetic than we ever imagined. We're living in a universe that's constantly exploding in small, brilliant ways we're only just beginning to see. And here's the strangest part. We don't know if FRBs have always been happening or if they're a recent phenomenon. They could have been occurring since the early universe, since the first stars formed and died. Or they could be new, a sign that the universe has entered a different phase. We have no way to know. We only started looking in the right way with the right instruments in the last 2 decades. Before that, FRBs could have been flashing across the sky every night invisible to us. Like cosmic fireworks we didn't have the eyes to see. There's something poetic about that, isn't it? The idea that the universe has been performing this brilliant light show for billions of years and we only just noticed. That reality is richer, stranger, more spectacular than our theories allowed. That every time we build a better telescope, every time we look a little more carefully, we find something that makes us rethink everything. The search for FRBs has become a major focus of modern astronomy. New telescopes are being built specifically to catch them. The Canadian Hydrogen Intensity Mapping Experiment, or CHIME, is a strange-looking array of half-pipes in British Columbia, designed to scan the entire northern sky every day. It's detected hundreds of FRBs. The square-kilometer array being built in Australia and South Africa will be sensitive enough to detect FRBs from across the entire observable universe. We're entering an era where we might catch thousands, maybe tens of thousands of these bursts every year. And with that data, maybe we'll finally understand what's happening. Maybe the mystery will resolve into something beautiful and comprehensible. Or maybe it won't. Maybe FRBs will remain strange. Maybe the universe will keep its secrets a little longer. Maybe that's okay. Because the not knowing is part of what makes this wonderful. The sense that we're at the edge of understanding. That the cosmos still has surprises. That we're living through a time of discovery when the rules are being rewritten and anything seems possible. Fast radio bursts. Milliseconds of brilliance. Cosmic shouts from the deep. They've changed how we think about the universe. They've shown us that even in the emptiest reaches of space, even in the darkest voids between galaxies, things are happening. Energy is flowing. Events are unfolding. The universe is alive with activity we never suspected. And every burst we detect is a reminder that there's more to learn, more to discover, more to wonder about. The cosmos keeps speaking, and we're finally learning to hear its fastest, brightest words. But speed and brightness aren't the only ways the universe can confuse us. Sometimes it's not what we hear from space that puzzles us. Sometimes it's what we think we hear, only to discover we've been listening to ourselves all along. The next signal we encountered taught us a different kind of lesson, one about humility, careful observation, and the very human tendency to see patterns where none exist. Sometimes the most mysterious signals in the universe come from the closest place imaginable, your kitchen. For 17 years, scientists at one of the world's most prestigious observatories detected strange bursts of radio energy that seemed to defy explanation. They had all the hallmarks of cosmic phenomena: sudden, powerful, unexplained. Papers were written, theories proposed. The signals were given a name from Greek mythology, peritons, after winged creatures that cast the shadow of a man. And then, in 2015, someone checked the microwave. Yes, the microwave. And the entire mystery collapsed into something almost embarrassingly simple. Almost. It started in 1998 at the Parkes Observatory in New South Wales, Australia. Parkes is home to one of the Southern Hemisphere's most important radio telescopes, a 64-meter dish that's been scanning the skies since 1961. Its detected pulsars helped communicate with the Apollo moon missions, and even played a starring role in the movie The Dish. It's a serious scientific instrument, operated by serious scientists doing serious work. So, when strange radio bursts started appearing in the data, bursts that looked almost like fast radio bursts, but not quite, people paid attention. The signals were powerful milliseconds long and seemed to come from the sky. But there was something odd about them. They only appeared during working hours, daytime, never at night, never on weekends. And they showed up across multiple receivers simultaneously, which suggested a local source, not a distant cosmic one. Scientists are trained to be skeptical. They know that most anomalies aren't revolutionary discoveries. They're equipment malfunctions, software glitches, or interference from human activity. So, the park's team investigated. They checked their instruments, ran diagnostics, looked for patterns. The signals didn't match known sources of radio interference. They weren't from cell phones or radio stations or passing aircraft. They were brief, broadband, and intense. They had characteristics similar to FRBS, but with subtle differences. The frequency structure was wrong. The dispersion measure was too low. These weren't coming from billions of light years away. They were local. But local didn't mean understood. For years, perytons were a nuisance, an unexplained background signal that contaminated real observations. Some researchers suspected they were atmospheric in origin, perhaps related to lightning or unusual weather patterns. Others thought they might be instrumental artifacts, quirks of how the telescope processed data. A few wondered if they represented a genuinely new phenomenon, something happening in Earth's ionosphere or magnetosphere. Papers were published suggesting various mechanisms. None of them quite fit. The perytons remained mysterious, frustrating, and weirdly persistent. Then came 2015, a team led by Emily Petrov, an astronomer working at Swinburne University, decided to settle the matter once and for all. They installed a new interference monitoring system at Parks 1, sensitive enough to catch even the faintest signals from nearby electronic devices. The goal was simple: detect a peryton in real time and immediately identify its source. On January 2015, they got their chance. A peryton appeared, and the monitoring system lit up. The source was inside the observatory building. Specifically, it was coming from the staff kitchen. The culprit, a microwave oven. But not just any microwave usage. The key was in how people used it. When someone opened the microwave door before the timer finished, before the magnetron shut down properly, a brief burst of microwave radiation would escape. That burst at 2.4 gigahertz was within the frequency range the telescope monitored. And because the telescope's receivers were so sensitive, designed to catch the faintest whispers from across the universe, they had no trouble picking up a relatively strong signal from just a few hundred meters away. The signal would propagate through the atmosphere, scatter slightly, and appear in the data as if it came from multiple directions at once. A perfect illusion. A cosmic mystery born from someone's impatience with leftover lunch. The discovery was published in the journal Monthly Notices of the Royal Astronomical Society. The reaction in the astronomy community was mixed, relief certainly, one less unexplained phenomenon to worry about, but also a kind of collective embarrassment. 17 years, dozens of detections, multiple research papers, and the answer was a microwave oven that people were opening prematurely. It felt almost too mundane, too silly. How could professional astronomers miss something so obvious? But here's the thing. They didn't miss it out of incompetence. They missed it because they were looking in the wrong direction. Science is built on assumptions. When you detect a signal with a radio telescope, you assume it's astronomical. That's what the telescope is designed to find. You assume someone in the facility knows enough not to interfere with observations. You assume the shielding is adequate, the protocols are followed, the environment is controlled. Most of the time, those assumptions are correct, but sometimes they're not. And when they're not, You can spend years chasing a ghost. The parrot in story teaches us something important about the scientific method. It's not enough to detect a signal. You have to verify its origin. You have to eliminate every possible source of error, no matter how unlikely or embarrassing. You have to be willing to look foolish to check the obvious, to question your assumptions. Because the universe doesn't care about your ego. It doesn't care if the answer is profound or prosaic. Truth is truth, whether it comes from a dying star or a kitchen appliance. Think about how many times in your own life you've assumed something was complicated when the answer was simple. How many times did you overlook the obvious? But the story doesn't end there, because the Periton investigation revealed something else, something more subtle but equally important. Even after they identified the microwave as the source, questions remained. Why did some bursts look different from others? Why did the signals show slight variations in frequency and intensity? The answer involved the specific model of microwave, how old it was, whether the door seal was degraded even the exact moment during the cooking cycle when someone opened it. Each variable changed the signal slightly, which means that what seemed like a single phenomenon, Peritons, was actually a collection of related but distinct events, each with its own characteristics. This is a common pattern in science. We give names to things before we fully understand them. We categorize. We simplify. And sometimes that's necessary. You can't investigate what you can't name, but the names can also mislead us. They can make us think we're dealing with one thing, when we're actually dealing with many. Fast radio bursts might be like that. We call them all FRBs, but maybe they're a dozen different phenomena that just happen to look similar. Maybe some are from magnetars, some from colliding neutron stars, some from processes we haven't even theorized yet. The label doesn't guarantee unity of cause. After the microwave discovery, scientists went back through 17 years of Parkes data and identified 26 separate Periton events. Every single one occurred during daytime working hours. Every single one corresponded with periods when staff were in the building. The correlation was perfect. And once they knew what to look for, they found similar interference at other observatories. Green Bank in West Virginia, Arecibo in Puerto Rico. Anywhere there were sensitive radio telescopes and microwaves nearby, there was the potential for these false signals. It was a systematic problem that had gone unnoticed because everyone assumed the signals had to be astronomical. There's a deeper lesson here about how we search for extraterrestrial intelligence. When SETI researchers scan the skies for artificial signals, they're trying to distinguish between natural cosmic noise and deliberate transmissions from alien civilizations. But how do you know? How do you tell the difference between a pulsar's regular beat and an alien beacon? How do you separate a natural burst from an artificial one? The Periton affair shows how difficult this is. Even trained astronomers using sophisticated equipment can be fooled by their own technology. Imagine trying to identify an alien signal. It would need to be unmistakably artificial, a pattern nature couldn't produce, a mathematical sequence, prime numbers, a structure too organized to arise by chance. And even then you'd need to verify it. Check for terrestrial interference, confirm it with multiple independent observations. Make sure it's not someone's microwave. This brings up an interesting paradox. The more sensitive our instruments become, the more false positives we encounter. Modern radio telescopes can detect signals billions of times weaker than early ones. That's good for finding faint cosmic sources. But it also means they pick up interference from satellites, aircraft, cell towers, garage door openers, even the spark plugs in passing cars. Astronomers have become experts at filtering out these signals, building sophisticated algorithms that distinguish cosmic from terrestrial. But it's an arms race. As our technology gets better at detecting signals, our technology also gets better at creating interference. We're drowning in our own noise. Some observatories have responded by establishing radio quiet zones, areas where terrestrial transmissions are restricted or banned. The Green Bank Observatory sits in the National Radio Quiet Zone, a 13,000 square mile area in West Virginia, where radio transmissions are heavily regulated. No cell phones, no Wi-Fi, no wireless anything within a certain radius. It's one of the last places in the developed world where the electromagnetic spectrum is relatively clean, where you can listen to the universe without competing with human chatter. Even there, though, satellites pass overhead. Aircraft cross the sky. Perfect silence is impossible. The parks team, after solving the Perryton mystery, published recommendations for other observatories. Check your kitchen appliances. Monitor for local interference. Don't assume signals are cosmic just because they appear in your data. It seems obvious in hindsight. But hindsight is always clear. The challenge is seeing it in the moment, when you're immersed in data and patterns and the exciting possibility that you found something new. Here's what I find beautiful about the Perryton story. The scientists involved didn't hide their mistake. They didn't quietly remove the data and pretend it never happened. They published their findings openly, explaining exactly what went wrong and why. That's science at its best. Not perfect, not infallible, but honest, self-correcting, willing to admit error in the pursuit of truth. It's a reminder that scientists are human. They make mistakes, they get excited, they overlook things, but the system works because it's designed to catch those errors eventually. Someone will check, someone will question, someone will open the microwave door at the right moment and realize what's happening. And yet, even knowing all this, part of me wishes Perryton's had been something more exotic, something cosmic, something that revealed a new facet of the universe. Because that's the romantic dream, isn't it? That we'll stumble upon something that changes everything. That one day a signal will appear in the data, and it won't be a microwave or a satellite or a glitch. It will be real. It will be from out there, and it will rewrite our understanding of our place in the cosmos. Maybe we already have. Maybe somewhere in the mountains of data collected by telescopes around the world, there's a signal waiting to be recognized, a message, a beacon, a whisper from another world. We just haven't found it yet because we're still learning how to look, still learning how to separate the extraordinary from the ordinary, still learning in the most fundamental way how to listen. The Perryton phenomenon taught us humility. It taught us to check our assumptions, verify our sources, and never underestimate the mundane. But it also taught us persistence. Because even when the answer is disappointing, even when the mystery dissolves into something simple, the search continues. We keep building better instruments. We keep scanning the skies. We keep hoping that the next signal will be the one that matters. And maybe while we're busy checking microwaves and filtering interference, we'll catch something genuine. Something that isn't us talking to ourselves, but the universe talking back. Until then, we listen. We learn. We remain vigilant. Because you never know when the cosmos might actually have something to say. But not every mystery in space reveals itself through sudden bursts or fleeting signals. Some whispers have been traveling since the very beginning of time itself, carrying with them the oldest light in existence. And within that ancient glow, there are patterns that shouldn't be there. Shadows that suggest the universe remembers something from before it was born. There's a light older than stars, older than galaxies, older than almost everything except the universe itself. It fills every corner of space, invisible to our eyes, but detectable by our instruments. A faint glow cooler than frozen that's been traveling for 13.8 billion years. It's the afterglow of creation, the oldest signal we can ever hope to receive. And it should be uniform, smooth, the same temperature everywhere. But it's not. There are cold spots, strange alignments, patterns that shouldn't exist. And those patterns whisper something unsettling. The universe might remember something from before it began. In 1964, two scientists at Bell Laboratories in New Jersey were trying to eliminate noise from a large radio antenna. Arno Penzias and Robert Wilson were meticulous. They checked everything, calibrated their instruments, even cleaned out pigeon droppings from the antenna, thinking the birds might be causing interference. But the noise persisted, a faint hiss at microwave frequencies coming equally from every direction in the sky. It never changed, never faded. It was constant, uniform, and utterly mysterious. What they had discovered, though, they didn't know it yet, was the cosmic microwave background, or CMB, the echo of the Big Bang, the oldest light in the universe. They won the Nobel Prize for it in 1978, and they'd opened a window into the very first moments of existence. The CMB is what happens when you look at the universe in its infancy. About 380,000 years after the Big Bang, the universe had cooled enough for atoms to form. Before that moment, space was opaque, filled with a plasma so hot that light couldn't travel freely. But when atoms formed, light was released, a flash of radiation that filled all of space. And as the universe expanded, that light stretched, cooled, shifting from visible light to infrared to microwave. Today it's about 2.725 degrees above absolute zero, Kelvin. The coldest light you can imagine, and it's everywhere. In this room, in your body, in the deepest voids between galaxies. It's the background hum of reality itself. Scientists have mapped the CMB with extraordinary precision, first with satellites like COBE in 1989, then WMAP in 2001, and finally Planck from 2009 to 2013. These spacecraft measured tiny variations in the CMB's temperature. Tiny. We're talking about differences of a few millionths of a degree. But those tiny variations matter because they represent the seeds of everything. The slight density fluctuations that eventually grew into galaxies, stars, planets, and us. The CMB is a baby picture of the universe. And like any baby picture, it tells you about genetics, about origins, about what came before. Here's where things get strange. The CMB should be almost perfectly uniform. The Big Bang, according to standard cosmology, was smooth, homogeneous, the same everywhere. And for the most part, the CMB confirms this. Temperature variations are tiny and random, exactly as predicted. But there are anomalies, places where the temperature is slightly colder than it should be, patterns that align in ways that seem too deliberate to be coincidence, and no one can fully explain why. The most famous of these is the CMB cold spot, discovered in 2004 by WMAP and confirmed by Planck. It's a region of the sky about 10 degrees across, roughly 20 times the diameter of the full moon, where the temperature is about 70 microkelvins colder than average. That might not sound like much, 70 millionths of a degree, but in the context of the CMB, it's significant. It's outside the range of normal statistical fluctuation. Something made that spot colder, but what one possibility is that it's a super void, a massive region of space, perhaps a billion light years across, that's emptier than average. Light passing through such a void would lose energy, a phenomenon known as the integrated Sachs-Wolf effect. It would arrive at our detectors slightly cooler. Surveys have found evidence of a void in that direction, though not quite large enough to fully explain the cold spot. So maybe it's a combination, a void plus some other effect we don't understand. Or maybe the void is larger and denser than we thought. Or maybe it's not a void at all. Another theory is more exotic. What if the cold spot is the imprint of a collision? Not a collision of galaxies or stars, but a collision of universes. In some models of cosmology, our universe isn't alone. It's part of a multiverse, an infinite collection of bubble universes expanding into higher dimensional space. Occasionally, these bubbles collide, and when they do, they leave marks, bruises on the fabric of space-time. The cold spot could be such a bruise, evidence that before we existed, another universe brushed against ours and left a scar. It's speculative, unprovable with current technology, but it's not impossible. Do you ever wonder if reality is bigger than what we can see? If there are universes beyond ours forever out of reach? But the cold spot isn't the only anomaly. There's something called the axis of evil. No, not a geopolitical reference. an astronomical one. When scientists analyzed the largest scale patterns in the CMB, they found something bizarre. The quadrupole and octupole moments, which describe the largest temperature fluctuations, seem to be aligned with each other and with the plane of the solar system. This shouldn't happen. The CMB comes from the edge of the observable universe. It has nothing to do with our solar system. The alignment should be random, but it's not. It's organized, deliberate looking, as if the universe has an axis, a preferred direction, a structure that contradicts the fundamental assumption that space is the same in all directions. This discovery was so unexpected that scientists initially thought it was an error. Maybe dust in our galaxy was contaminating the signal. Maybe the instruments had a bias, so they checked. They accounted for foreground sources. They cross-referenced with multiple satellites. The alignment persisted. It's real, and no one knows what it means. Some have called it the most significant challenge to the standard cosmological model in decades. Others think it's a statistical fluke, a coincidence that looks meaningful but isn't. The debate continues. Kate Land and João Maguejo, physicists who studied this phenomenon, extensively described it as looking like the universe has handedness, a chirality, a preference for one orientation over another. If true, it would mean the Big Bang wasn't perfectly isotropic. Something broke the symmetry. But what and why does it align with our solar system? That part feels almost conspiratorial, as if the universe arranged itself around us. But that's absurd. We're not special. We're not central. The Copernican principle, one of the foundations of modern cosmology, says we occupy no privileged position. Yet, here's data suggesting a connection between the largest structures in the cosmos and our local neighborhood. It's deeply uncomfortable. One explanation involves topology. Maybe the universe isn't infinite. Maybe it wraps around on itself like the surface of a sphere or a torus. In such a universe, light from distant regions can take multiple paths to reach us, creating repeating patterns. Some of these patterns might align in specific ways depending on the universe's shape. It's elegant mathematically, but testing it requires observations beyond what we can currently achieve. So, it remains a possibility hanging in the space between theory and evidence. Another set of anomalies involves something called hemispherical asymmetry. When you divide the CMB into two hemispheres, one half is slightly warmer on average than the other. Again, this shouldn't happen. The universe should be the same in all directions. But it's not. One hemisphere is about 5.6 microkelvins warmer. Scientists have checked for instrumental errors, galactic contamination, even the motion of our solar system through space. None of these explain the asymmetry. It's a real feature of the CMB, and it suggests that the early universe was lopsided, that the Big Bang happened differently in different regions, or that we're seeing the influence of something beyond our observable universe, something that imprinted its signature on the cosmos before we existed. Planck, the most advanced CMB satellite ever built, confirmed all of these anomalies. It ruled out many potential explanations. It tightened the constraints, but it didn't solve the mysteries. If anything, it made them more concrete, more undeniable. The anomalies are there. They're measurable. They're consistent across different instruments and data sets. The question is not whether they exist, but what they mean. Some physicists think they're pointing to new physics, extensions of general relativity, modifications to the inflationary model of the early universe. Inflation is the idea that the universe underwent a brief period of exponential expansion in its first fraction of a second, smoothing out irregularities and setting up the conditions we observe today. It's a beautiful theory. It explains a lot. But maybe it's incomplete. Maybe inflation wasn't perfectly uniform. Maybe it was driven by multiple fields, each with slightly different properties, creating asymmetries that persist in the CMB. Or maybe there was something before inflation, a pre-Big Bang state, a contracting universe that bounced into expansion. Cyclic cosmology. echoes of a previous cosmos embedded in the microwave background. These ideas push the boundaries of what we can test. The CMB is the oldest signal we can observe. Beyond it lies the cosmic dark age, a period before the first stars formed, and before that, the opaque plasma of the early universe. We can't see further back with light. Not directly. We need other methods. Gravitational waves, perhaps, neutrinos, exotic particles predicted by theories we haven't confirmed yet. The CMB is a wall, and these anomalies might be shadows cast on that wall by events on the other side. Events we can infer but never witness. There's something almost haunting about that. The idea that we're looking at the oldest thing we can ever see, and it's telling us there's something older, something beyond. The universe had a beginning, but what came before that beginning? Did time itself start with the Big Bang, or is time more fundamental? Are we part of an eternal cycle, an infinite sequence of universes being born, expanding and collapsing, each leaving faint traces in the next? The anomalies don't answer these questions. They just make them more urgent. I want you to think about the temperature for a moment. 2.725 Kelvin. That's cold. Colder than anything on Earth. Colder than the emptiest parts of interstellar space. It's the temperature of the universe after 13.8 billion years of cooling. And it's uniform to 1 part in 100,000. That's astonishing. It means the early universe was incredibly smooth, incredibly well mixed. So much so that it's hard to explain how different regions separated by distances light couldn't have crossed in the time available ended up at the same temperature. This is called the horizon problem. Inflation solves it by saying everything was once close together in thermal contact before inflating apart. But the anomalies challenge this. They suggest the universe wasn't quite as smooth as we thought, that there were asymmetries, variations, memory, the cold spot, the axis of evil, the hemispherical asymmetry. Together they paint a picture of a universe that's subtly broken, not catastrophically. Not in a way that makes life impossible, but enough to make us question our assumptions. Enough to suggest that the story we tell about the Big Bang, about inflation, about the origin of everything, is missing pieces. Important pieces. And yet, the standard model of cosmology works. It predicts the CMB's overall structure with incredible accuracy. It explains the abundance of elements, the expansion rate, the formation of galaxies. The anomalies are small, statistically marginal in some cases. Maybe they're just noise. Maybe we're seeing patterns because we're pattern-seeking creatures evolved to find meaning in randomness. Maybe the universe doesn't care about our need for perfect symmetry. But I don't think that's the answer. I think the anomalies are real. I think they're telling us something. Maybe not about multiverses or cosmic collisions. Maybe something simpler and stranger. That the universe is more complex than our equations allow. That reality has layers we haven't uncovered. That every answer opens new questions, and that's okay. That's how knowledge grows. Not in straight lines, but in spirals circling back, finding deeper truths beneath the surface. The CMB will continue to be studied. New missions are planned. Ground-based telescopes, satellites, experiments designed to probe even finer details. Perhaps they'll resolve the anomalies. Perhaps they'll find new ones. Either way, we'll learn. We'll refine our models. We'll edge closer to understanding how it all began. And maybe we'll glimpse what came before. But while the cosmic microwave background whispers secrets from the dawn of time, there are signals arriving from much closer to home. Signals that seemed for a brief moment like they might be the answer to the oldest question we've ever asked. Signals that came from the direction of the nearest star and made us wonder if we were finally hearing from neighbors we never knew we had. 4.2 light-years away, there's a star, small, red. Unremarkable except for one thing, it's the closest star to our sun. And orbiting that star is a planet. Proxima Centauri b, a world in the habitable zone where liquid water could exist. where life theoretically might take hold. In 2019, a radio telescope pointed in that direction detected something unusual, a narrow signal at 982.002 megahertz. It appeared only when the telescope aimed at Proxima Centauri. When it looked away, the signal vanished. For months, scientists analyzed it in secret, afraid to hope, afraid to speak. Because if this signal was real, if it was coming from our nearest stellar neighbor, it would mean we are not alone. It would change everything. The signal was designated BLC1. Breakthrough Listen. Candidate 1. Breakthrough. Listen is a 10-year, $100 million initiative funded by Russian billionaire Yuri Milner and launched in 2015. Its goal is simple: to conduct the most comprehensive search for extraterrestrial intelligence ever undertaken. They use the best telescopes, the most sensitive instruments. They scan millions of stars listening for any hint of artificial signals. Most of what they find is noise. Interference from satellites, aircraft, human technology. But occasionally something stands out, something that makes researchers lean forward and wonder. BLC1 was detected during observations of Proxima Centauri, conducted between April and May 2019, using the Parkes Radio Telescope in Australia, the same telescope, incidentally, that gave us the Perryton microwave mystery. But this time, the signal looked different. It was narrow band, only a few hertz wide. Natural astronomical sources are usually broadband spread across many frequencies. Artificial sources like radio transmitters are narrow, focused. This signal was focused, and it showed something called a drift. The frequency changed slightly over time, shifting from 982.002 megahertz down to 982.001 megahertz over the course of several hours. This is exactly what you'd expect if the source was on a planet rotating on its axis or orbiting a star. Doppler shift. The same effect that makes an ambulance siren change pitch as it passes you. The signal was moving, and it was moving in a way consistent with being on a planetary surface. The excitement within the Breakthrough Listen team was palpable but contained. They had been through this before, signals that looked promising at first, but turned out to be terrestrial interference, cell phones, GPS satellites. Radio broadcasts reflected off debris. The universe is full of false alarms, so they kept it quiet, they analyzed, they checked. They followed protocols designed to weed out mistakes. And for months, BLC1 remained intriguing, unexplained, possible. The signal appeared only when the telescope was pointed at Proxima Centauri. When it pointed at nearby reference positions, empty patches of sky used for comparison, the signal disappeared. This is a critical test. If a signal is terrestrial interference, it shows up everywhere. If it's cosmic, it should only appear from one specific direction. BLC1 passed this test, or seemed to. It appeared in 5 separate 30-minute observation sessions, all when the telescope was aimed at Proxima, never during the off-source observations. The pattern was consistent, deliberate-looking, as if something near Proxima Centauri was broadcasting at 982 megahertz, and we had caught it. News of BLC1 leaked in December 2020. The Guardian published an article describing the signal and the search for its origin. The story went viral. Headlines appeared worldwide. Had we finally detected aliens? Was this the moment humanity had been waiting for? Scientists urged caution. They always do. Extraordinary claims require extraordinary evidence. BLC1 was interesting? Yes. But interesting isn't proof. It needed more scrutiny, more analysis, more checks. The truth when it came was both disappointing and instructive. In October 2021, after nearly 2 years of investigation, the Breakthrough Listen team published their findings in the journal Nature Astronomy. BLC1 was not from Proxima Centauri. It was terrestrial interference. Specifically, it was radio frequency interference, or RFI, from electronic equipment. But not just any equipment. The signal had characteristics that mimicked an extraterrestrial source so well that it fooled experienced researchers for months. It appeared only during on-source observations because of a subtle timing coincidence. The interference happened to occur at moments when the telescope was pointed at Proxima. Pure chance. A statistical fluke that created a pattern where none existed. How did they figure this out? By going deeper. They analyzed not just the 5 observations where BLC-1 appeared, but all the data from that observing campaign. Hundreds of hours, millions of data points. And they found something. The signal wasn't unique. There were similar signals at nearby frequencies. 982.001 megahertz. 982.003 megahertz. A whole family of narrowband signals clustered around the same region of the spectrum. And these signals appeared at other times during observations of other stars, not just Proxima. The pattern broke. BLC-1 wasn't special. It was part of a larger background of interference that the initial analysis had missed. Further investigation revealed the likely source. Electronics near the telescope. Computers, perhaps. Signal processing equipment. Something generating radio noise at frequencies that happened to overlap with the telescope's observing band. The exact source was never pinpointed. It didn't need to be. The evidence was clear. BLC-1 was human-made, local. Not a message from the stars, but noise from our own technology. The dream dissolved. The excitement faded. Another false alarm. But here's the interesting part. The researchers didn't hide this. They didn't bury the data. They published it, openly, transparently. They explained exactly how they were fooled and what they learned. Because science isn't about being right. It's about finding truth. And sometimes truth means admitting you were wrong. The BLC-1 episode became a case study in how to properly analyze candidate signals, how to avoid confirmation bias, how to dig deeper even when the initial results look promising. It was a lesson in skepticism and rigor, and in a strange way it was as valuable as a genuine detection would have been. Think about what happened here. A signal appeared. It had the characteristics we associate with artificial transmissions: narrow band, drifting frequency, directional. It came from the direction of the nearest potentially habitable planet. Every box was checked, every expectation met. And yet, it was still wrong. This tells us something important about the search for extraterrestrial intelligence. It's hard, really hard. The galaxy is awash in radio noise, both natural and artificial. Distinguishing a genuine alien signal from the background requires extraordinary care. You can't just find a signal and declare success. You have to eliminate every possible alternative explanation. Every single one. And even then, you need confirmation, independent detection, replication. Science is a process, not a moment. Proxima Centauri itself is a fascinating target. It's a red dwarf smaller and cooler than our Sun, with about 12% of the Sun's mass. Red dwarfs are the most common type of star in the galaxy. They burn slowly, living for trillions of years. If life exists around them, it could have far more time to develop than life around Sun-like stars. Proxima Centauri b was discovered in 2016. It orbits close to its star, completing one orbit every 11.2 days. Because the star is cool, this close orbit still places the planet in the habitable zone. Surface temperatures could allow liquid water. Could. We don't know much about the planet's atmosphere or whether it even has one. Red dwarfs are active. They flare. They emit radiation that might strip away atmospheres from nearby planets. Proxima Centauri b could be a lush, habitable world. Or it could be a barren rock scoured by stellar winds. We don't know. But it's close. 4.2 light-years. That's practically next door in cosmic terms. The nearest star system beyond our own. If we ever send a probe to another star, Proxima Centauri is the most likely target. Breakthrough Star Shot. Another project funded by Yuri Milner aims to do exactly that. Send tiny lightweight probes accelerated by powerful lasers to 20% the speed of light. At that speed, they'd reach Proxima in about 20 years. They'd fly past, take pictures, send data back. It would take another 4.2 years for the signals to reach Earth. So, launch today, receive data in about 25 years, a generation. But doable. And if there's life on Proxima Centauri b, we might see it, or at least see signs. Oxygen in the atmosphere, vegetation, city lights, something. Do you think we'll find life there? Or does the universe keep its neighbors hidden, just out of reach? The BLC1 episode highlights a deeper issue in SETI, the Great Silence, also known as the Fermi Paradox. Enrico Fermi famously asked, "Where is everybody?" If the galaxy is billions of years old, if intelligent life is even moderately common, we should see evidence. Radio signals, Dyson spheres, megastructures, self-replicating probes, something. But we don't. The sky is quiet. We've listened to thousands of stars. We've scanned vast regions of the galaxy. We've found nothing, no unambiguous signals, no clear evidence of technology, just silence. Why? There are many possible answers. Maybe intelligent life is rare. Maybe it doesn't last long. Maybe civilizations destroy themselves before they can colonize the stars. Nuclear war, climate collapse, artificial intelligence gone wrong. Maybe the great filter lies ahead of us, not behind. Or maybe they're out there, but not broadcasting. Maybe radio is primitive. Maybe advanced civilizations use communication methods we haven't discovered yet. Quantum entanglement, neutrino beams, gravitational wave modulation, technologies we can't even imagine. Or maybe they're hiding, staying quiet, afraid of something, afraid of us. Or maybe we're alone. Maybe Earth is the only place in the galaxy where life arose and developed intelligence. It's possible. The conditions required for life are specific: liquid water, stable climate, protection from radiation, a moon to stabilize the planet's tilt, a gas giant to sweep up asteroids. We don't know how rare this combination is. We don't know if life is inevitable given the right conditions, or if it's a fluke, a cosmic accident that happened once and never again. The thought is both lonely and profound, that we might be the universe's only way of knowing itself. That consciousness, intelligence, the ability to ask questions and seek answers might exist nowhere else. It would make us precious, fragile, responsible for preserving something irreplaceable. BLC. One gave us hope briefly. The possibility that our nearest neighbor might be home to someone, that we could reach out and make contact, that the silence could end. But the signal was a mirage, a reflection of ourselves. And so, the search continues. We keep listening, keep scanning, keep hoping. Because even one detection, one genuine signal would answer the question. We are not alone, and that knowledge would reshape everything. Philosophy, religion, science, our understanding of our place in the cosmos. The Breakthrough Listen project continues. They've expanded their search. They're now looking at 1 million nearby stars. They're scanning the galactic plane. They're analyzing data with machine learning algorithms that can identify patterns humans might miss. They're searching not just for radio signals, but for optical pulses, laser beacons, any sign of technology. And they're being more careful, more rigorous. The BLC1 experience taught them valuable lessons: how to filter interference, how to avoid false positives, how to remain skeptical even when the data looks promising. And maybe that's the real takeaway. Not that we failed to find aliens at Proxima Centauri, but that we're getting better at looking. We're refining our methods. We're learning what to look for, and just as importantly, what to ignore. Each false alarm teaches us something. Each candidate signal eliminated brings us closer to recognizing the real thing when it finally appears. If it appears. The universe is vast. The distances are enormous. The timescales are staggering. Even if there are civilizations out there, even if they're broadcasting, the chances of us hearing them at the right moment, from the right direction, at the right frequency, are slim. It's like trying to have a conversation across an ocean, shouting into the wind, hoping someone on the other side happens to be listening. The odds are against us, but we try anyway, because the potential reward is too great to ignore, because curiosity demands it, because we are at our core explorers, seekers, creatures who look at the stars and wonder what's out there. BLC-1 was a whisper that turned out to be an echo of our own voice. But the silence is not empty. It's full of possibility, full of questions waiting for answers. And somewhere in that silence, perhaps, is a signal we haven't found yet. A message, a greeting, a sign that we are part of something larger. We listen, we wait, we hope, and the search goes on. But the universe doesn't always speak in radio waves or narrow band signals. Sometimes it announces itself with violence, with bursts of energy so powerful, so overwhelming, that they momentarily become the brightest objects in the entire cosmos. And when these events occur, they remind us that the universe is not just mysterious, it's dangerous, spectacular, and capable of forces that dwarf our comprehension. On March 19th, 2008, something halfway across the universe exploded. For 10 seconds, it was brighter than 1 trillion suns, brighter than entire galaxies. So bright that if you had been looking at the right patch of sky with the naked eye, you would have seen it, 7.5 billion light years away. Visible without a telescope. The light from that explosion had been traveling since long before Earth existed. And when it finally arrived, it briefly became the most distant object ever seen with human eyes alone. The universe had screamed, and for once we heard it loud enough to see. These are gamma-ray bursts, the most violent explosions in the universe since the Big Bang itself. They last anywhere from milliseconds to several minutes, but in that brief window they release more energy than our sun will produce in its entire 10 billion year lifetime. More energy than 100 supernovae combined. They are cosmic catastrophes, deaths of stars, collisions of the densest objects imaginable. And for decades, we had no idea what they were. The story begins strangely enough with nuclear weapons. During the Cold War, the United States and Soviet Union signed the Partial Nuclear Test Ban Treaty in 1963, agreeing not to test nuclear weapons in the atmosphere, in space, or underwater. But how do you verify compliance? How do you know if your adversary is secretly detonating bombs in orbit? The answer: you watch for gamma rays. Nuclear explosions produce brief flashes of gamma radiation. So, the US launched a series of satellites called Vela, designed to orbit Earth and monitor for these telltale signatures. They were spy satellites, essentially. Eyes in the sky, watching for cheating. On July 2nd, 1967, 2 Vela satellites, Vela 3 and Vela 4, both detected a flash of gamma rays. But the signature was wrong. It lasted too long. The spectrum was different, and most tellingly, the satellites detected it at slightly different times. If the source had been on Earth or in near-Earth orbit, both satellites would have detected it simultaneously. But there was a delay, a small one, which meant the source was far away, very far away. The gamma rays came from deep space. The military kept this classified for years. They weren't sure what they'd found. They didn't want to reveal the capabilities of their satellites. But eventually, in 1973, scientists published the discovery in the Astrophysical Journal. They had detected 16 gamma-ray bursts between 1969 and 1972, short, intense flashes from random directions in the sky. Unlike anything known, pulsars produced regular pulses. Supernovae brightened slowly. These were different, sudden, explosive, mysterious. and they opened a new window into the universe's most extreme events. For decades, astronomers debated what caused gamma-ray bursts. The distances were uncertain. Were they local within our galaxy or cosmological from across the universe? The debate was fierce. If they were local, they represented relatively small explosions nearby. If they were cosmological, they had to be extraordinarily powerful to be visible from billions of light years away. In 1997, the Italian-Dutch satellite Bepo-SAX finally settled it. It detected a gamma-ray burst designated GRB 970228 and quickly localized its position. Ground-based telescopes followed up and found a fading optical afterglow in a distant galaxy. The burst was cosmological, billions of light years away, which meant it had released an almost incomprehensible amount of energy. Scientists now recognize two main types of gamma-ray bursts: short bursts lasting less than 2 seconds and long bursts lasting more than 2 seconds. They have different origins. Short bursts come from the collision of neutron stars or a neutron star merging with a black hole. Long bursts come from the collapse of massive stars, at least 25 times the mass of our Sun, in a specific type of supernova called a hypernova or collapsar. In both cases, the result is the same: a catastrophic release of energy focused into narrow jets that shoot out at nearly the speed of light. If Earth happens to lie in the path of one of these jets, we see a gamma-ray burst. If we're off to the side, we might see a dimmer event, or nothing at all. We're witnessing the universe's most violent deaths, but only when they're pointed directly at us. Let's talk about GRB 080319b, the one visible to the naked eye. It was detected by NASA's SWIFT satellite on March 19, 2008. SWIFT is designed specifically to catch gamma-ray bursts. It detects the gamma rays, then rapidly swivels to point its optical and X-ray telescopes at the source, capturing the afterglow before it fades. GRB 080319b was extraordinary. It peaked at a visual magnitude of 5.8, just barely bright enough to see without a telescope, if you knew exactly where to look and had perfect dark skies. The burst came from a galaxy 7.5 billion light-years away. That light left its source when the universe was less than half its current age, and it was still bright enough to be visible to the unaided human eye. Think about that. You're standing outside on a clear night. You look up, and for a few seconds you can see an explosion that happened before the solar system existed, before Earth coalesced from dust. The photons hitting your retina traveled across more than half the observable universe to reach you. It's humbling, awe-inspiring, a reminder that we are connected to the cosmos in ways we rarely consider. But GRB 080319b isn't the record holder anymore. That title belongs to GRB 221009a, detected on October 9, 2022. Astronomers quickly nicknamed it the Boat, the brightest of all time. It was so intense it temporarily blinded gamma-ray detectors on multiple satellites. The instruments saturated, overloaded. They couldn't measure the peak brightness because it exceeded their design limits. This is like trying to measure the sun's brightness with a camera meant for photographing candles. The burst came from about 2.4 billion light-years away, closer than GRB 080319b, but far more energetic. It released an estimated 10 to the 54th ergs of energy. That's a 1 followed by 54 zeros. For comparison, the sun's total energy output over its entire lifetime is about 10 to the 52 ergs. The boat released 100 times more energy than the sun's entire life in just a few hundred seconds. The boat also did something unusual. It disrupted Earth's ionosphere. The ionosphere is a layer of charged particles high in our atmosphere created by solar radiation. When the gamma rays from the boat hit Earth, they ionized atoms in the lower ionosphere, creating a disturbance that was measurable by radio instruments. A gamma ray burst from 2.4 billion light years away affected our planet's atmosphere. It's almost unbelievable, and it raises a disturbing question. What would happen if a gamma ray burst occurred closer? Much closer? Gamma ray bursts are directional. The energy is focused into jets beamed like a lighthouse. If you're in the beam, you see the burst. If you're not, you don't. This means most gamma ray bursts we detect are aimed directly at us, and it means we're probably missing thousands of bursts that are pointed elsewhere. But it also means that if a gamma ray burst happened in our galaxy, aimed at Earth, the consequences could be catastrophic. The gamma rays would strip away the ozone layer. Without ozone, ultraviolet radiation from the sun would reach the surface unfiltered. It would damage DNA, kill phytoplankton in the oceans, disrupt food chains. A nearby gamma ray burst could cause a mass extinction. Some scientists have speculated that past extinction events on Earth might have been triggered by gamma ray bursts. The Ordovician extinction about 450 million years ago wiped out roughly 85% of marine species. The cause is unknown. A gamma ray burst is one possibility, not certain, not proven, but possible. There's some evidence. Isotopes in ancient rocks that suggest a burst of radiation from space. But the data is ambiguous. We can't know for sure. The universe doesn't leave clear fingerprints for events that happened hundreds of millions of years ago. How would you feel knowing that at any moment a gamma ray burst could end everything, and we'd never see it coming? Fortunately, gamma ray bursts are rare. In our galaxy, they probably occur only once every few 100,000 to 1,000,000 years, and the chances of one being aimed directly at Earth are slim. Space is vast. The galaxy is big. The odds are in our favor, but not zero, never zero. There are stars in our galaxy that could produce gamma ray bursts. WR 104. A Wolf-Rayet star about 8,000 light-years away is one candidate. It's massive, unstable, and rotating rapidly. Some models suggest it could go hypernova and produce a gamma ray burst, and its rotation axis might be pointed toward Earth. Or it might not. The observations are uncertain. We don't know. And even if it is pointed at us, we don't know when it will explode. Could be tomorrow. Could be 100,000 years from now. The universe doesn't warn us. But let's not dwell on doom. Let's focus on the science. Because gamma ray bursts have taught us incredible things. They've shown us how matter behaves at the absolute extremes of density and energy. When a neutron star forms, atoms collapse. Electrons and protons merge into neutrons. A teaspoon of neutron star material weighs about 1 billion tons. These objects are so dense that if you dropped something onto the surface from a height of 1 meter, it would hit with the energy of a nuclear bomb. And when two of these collide, they don't just explode. They warp space-time. They create gravitational waves, ripples in the fabric of reality itself. In 2017, something extraordinary happened. For the first time, scientists detected both gravitational waves and gamma rays from the same event. A short gamma ray burst, designated GRB170-817A, coincided with a gravitational wave signal detected by LIGO and Virgo, the observatories that measure these ripples in space-time. The source was two neutron stars merging 130 million light-years away. This was the birth of multi-messenger astronomy. We didn't just see the explosion, we felt it. We heard the universe's fabric vibrate. And we watched the aftermath as telescopes around the world observed the kilonova, the radioactive fireball produced by the collision. That event taught us where heavy elements come from. Gold, platinum, uranium. They're forged in neutron star collisions. The gold in your jewelry, the platinum in electronics, was created in explosions like this and scattered into space, eventually finding its way into the dust cloud that formed our solar system. Gamma ray bursts are also cosmic yardsticks. Because they're so bright, we can see them from across the universe. They've been detected from galaxies more than 13 billion light-years away. shining when the universe was less than 1 billion years old. By studying these ancient bursts, we learn about the early universe, about the first generations of stars, about how galaxies formed and evolved. Each burst is a snapshot, a frozen moment from cosmic history delivered to us in a flash of light. There's something poetic about gamma ray bursts. They are both endings and beginnings, the death of a star, the birth of a black hole, the creation of elements, the seeding of space with the raw materials for future planets, future life. They are violent, yes, destructive, but also generative, creative. The universe builds by destroying. It creates by tearing apart. And in those moments of destruction, it shines brighter than anything else. It announces itself. It screams into the void, and we small and fragile listen. We've cataloged thousands of gamma ray bursts now. Swift alone has detected over 1,000. We've measured their distances, their energies, their spectra. We've watched their afterglows fade over hours and days. We've learned to predict which stars might produce them. We've built model simulations theories. But they still surprise us. The boat was unexpected. Its intensity exceeded predictions. It reminded us that the universe is not fully understood, that even phenomena we've studied for decades can still astonish us. And there are mysteries remaining. Some gamma ray bursts don't fit our models. Ultra-long bursts that last for hours. Bursts with unusual light curves. Bursts from galaxies that shouldn't produce them. Each anomaly is a clue, a hint that our understanding is incomplete, that there are mechanisms we haven't considered, processes we haven't imagined. The universe keeps its secrets close. It reveals them slowly, one explosion at a time. Gamma ray bursts are the loudest events in the universe. They are shouts that echo across billions of years. And every time we detect one, we learn something new. About matter, about energy, about the life and death of stars, about the fundamental forces that shape reality. They are laboratories, natural experiments conducted on scales we could never replicate, and they remind us that the universe is dynamic, changing, evolving, that even now, billions of years after the Big Bang, extraordinary things are happening. Stars are dying, black holes are forming, energy is being released in quantities that dwarf our comprehension. The cosmos is alive with violence and beauty, and we are fortunate enough to witness it. But not all cosmic mysteries arrive with such overwhelming force. Some appear quietly, almost politely, as a gradual dimming of light. A star that forgets for reasons unknown how to shine steadily. And when that star's strange behavior was discovered, it sparked one of the most captivating debates in modern astronomy. A debate about dust debris and the tantalizing possibility of technology on a scale we've only dreamed of. There's a star 1,470 light-years away that doesn't follow the rules. It dims, suddenly, dramatically. Not in the smooth, predictable way planets cause when they pass in front of their suns, but irregularly, chaotically, sometimes by 22%. That's enormous. No planet could block that much light, no comet, no known astronomical phenomenon. For a while, scientists considered something extraordinary, something artificial, the possibility that an advanced civilization had built structures around the star, massive structures, engineering on a scale that would make our greatest achievements look like sandcastles. The internet exploded with speculation. Was this it? Had we finally found them? The star was given a name, Tabby's star, and it became one of the most mysterious objects in the sky. The star's official designation is KIC 8462852. KIC stands for Kepler Input Catalog because it was observed by NASA's Kepler Space Telescope. Kepler launched in 2009 with a single mission to find planets around other stars. It did this by staring at a patch of sky containing about 150,000 stars, measuring their brightness continuously for years. When a planet passes in front of its star, it blocks a tiny fraction of the light. the brightness dips. Kepler measured these dips with extraordinary precision. Most are small, a fraction of a percent. Regular, periodic. The signature of a planet in a stable orbit. But KIC 8462852 was different. The dips were huge, irregular, aperiodic. They didn't repeat on a predictable schedule. One dip might be 15%, the next 22%, the next just a few percent. And the shapes were strange. Not the smooth U-shaped curves you'd expect from a spherical planet, but jagged, asymmetric, chaotic. Something was passing in front of the star, something big, something complex. But what the discovery was made by citizen scientists. Kepler produced so much data that professional astronomers couldn't analyze it all. So they turned to the public. A project called Planet Hunters invited volunteers to examine light curves looking for interesting patterns. In 2011, several volunteers flagged KIC 8462852 as unusual. It took years for professional astronomers to follow up. When they did, they were baffled. Tabitha Boyajian, an astronomer at Yale University, led the investigation. The star was later nicknamed Tabby's Star in her honor. In 2015, Boyajian and her team published a paper describing the anomalies, and the world took notice. The paper was titled, "Where's the Flux?" It detailed the strange dimming events. The largest occurred in 2011 and 2013. The 2011 event saw the star dim by about 15% over a week. The 2013 event was even more dramatic. A series of dips, including one that blocked 22% of the star's light. No known planet is large enough to cause that. Jupiter, the largest planet in our solar system, would block about 1% of the sun's light if it passed in front. To block 22%, you'd need something enormous, or many things. A swarm. Boyajian and her team considered natural explanations. A cloud of comets, a shattered planet, debris from a recent collision. None of them fit perfectly. Comets are icy. They sublimate, releasing gas and dust as they approach a star. But the star showed no excess infrared emission, which you'd expect from warm dust. The dimming events were too large, too irregular. And there was another problem. Historical data showed the star had been dimming overall for more than a century. Photographic plates from the 1890s compared to modern measurements showed a slow, steady decrease in brightness. About 20% over 100 years. That's not normal. Stars don't just fade like that. Not sun-like stars in their prime. This is where things got speculative. Jason Wright, an astronomer at Penn State, suggested an idea that captured imaginations worldwide. What if the dimming was caused by megastructures, specifically a Dyson swarm? The concept comes from physicist Freeman Dyson, who proposed in 1960 that advanced civilizations might eventually build structures around their stars to capture energy. Not a solid shell, that's physically unstable, but a swarm of solar collectors. Millions or billions of satellites orbiting the star, absorbing its light and converting it to usable energy. If such a swarm were under construction, you might see a regular dimming as more structures were added. And if the civilization was truly advanced, the scale could be enormous. The media ran with it. Headlines proclaimed, "Have we found an alien megastructure?" The idea was thrilling, tantalizing. But most scientists urge caution. Extraordinary claims require extraordinary evidence. And there were natural explanations still worth exploring. The Dyson swarm hypothesis was interesting, but should be a last resort. Something you consider only after eliminating every other possibility. SETI researchers pointed radio telescopes at Tabby's star, listening for signals. They found nothing. No narrowband transmissions. No obvious signs of technology. The star itself is an F-type main sequence star, slightly larger and hotter than our Sun, about 1. 4 times the Sun's mass. It's relatively young, a few billion years old. Nothing obviously unusual except the dimming. If there were a megastructure, you'd expect to see waste heat. Infrared radiation from the energy the civilization couldn't fully utilize. Observations in infrared showed some excess, but not enough. Not the massive amounts you'd expect from a Dyson swarm. The signal was more consistent with dust. In 2017, Tabby's star dimmed again. This time, astronomers were ready. They organized a global campaign. Telescopes around the world observed simultaneously at multiple wavelengths: optical, infrared, radio. And they found something crucial. The dimming was wavelength dependent. Blue light was blocked more than red light. This is the signature of dust. Small particles preferentially scatter shorter wavelengths. If the dimming were caused by a solid object like a planet or a megastructure, all wavelengths would be affected equally, but dust scatters light differently. This was a major clue. Whatever was blocking the star's light, it was dusty, not solid, not artificial. Further analysis suggested a cloud of uneven dust, perhaps from comets, perhaps from a disrupted planet. The dust wasn't in a uniform disk, but in clumps irregularly distributed. This explained the chaotic dimming pattern. As the star rotated, or as the dust orbited different amounts passed in front from our perspective. The 2017 observations didn't solve the mystery entirely, but they narrowed the field. The Dyson swarm hypothesis became less likely. Not impossible, but less likely. But what about the long-term dimming, the century-scale fading that remained unexplained? Some researchers suggested it might be an artifact. Errors in the historical photographic data. Old plates are tricky to calibrate. Different telescopes, different emulsions, different observing conditions. Maybe the star hadn't dimmed at all. Maybe our measurements were wrong. Other studies, though, confirmed the trend. The star does seem to be dimming over long time scales. Why? One possibility is a long period variation. Some stars pulsate or vary in brightness over decades or centuries. But Tabby's star doesn't fit known variable star categories. Another possibility is a very slow accumulation of dust, a gradual increase in the amount of material orbiting the star. Maybe a comet broke apart centuries ago, and we're seeing the ongoing dispersal of debris. Think about this. How would you react if you found evidence of a megastructure? Would you want it to be real, or would you prefer a natural explanation? In 2018, researchers proposed a specific scenario: a family of comets on highly elliptical orbits. Occasionally, one of these comets passes close to the star, heats up, and releases a massive cloud of dust and gas. The dust spreads out, creating the irregular dimming we observe. Over time, more comets disintegrate, adding to the cloud. This explains both the short-term dips and the long-term fading. It's not exotic, it's not aliens, but it fits the data. And in science, fit is what matters. Tabby's star taught us something important. Our first instinct when we see something strange is often to jump to the most exciting explanation. But excitement isn't evidence. The scientific method requires patience, rigor, the willingness to test boring hypotheses before entertaining extraordinary ones. The Dyson swarm idea was fun. It inspired people. It got the public interested in astronomy. But it was also a reminder that the universe is full of natural wonders that are strange enough without invoking aliens. And yet, the mystery isn't fully solved. The long-term dimming is still debated. The exact nature of the dust cloud is uncertain. There are other stars showing similar behavior. KIC 4110611, for example, nicknamed RIK 210. It shows irregular dimming that looks somewhat like Tabby's star, and there are probably more we haven't found yet. Kepler only observed a small patch of sky. If this kind of behavior is common, we'd expect to find many examples as we survey more stars. If it's rare, Tabby's star might be a unique, or at least unusual system. Either way, it tells us something about stellar evolution, planet formation, or comet dynamics. There's also the human element. Tabitha Boyajian didn't set out to find an alien megastructure. She was doing careful methodical science, analyzing light curves, looking for patterns. When the data showed something unexpected, she followed it. She published. She invited collaboration. She didn't sensationalize. The media did that. The public did that. And while it brought attention, it also brought pressure. Every new observation was scrutinized. Every hypothesis debated. She handled it with grace, engaging with the public, explaining the science, remaining open to possibilities while grounded in evidence. Tabby's star also highlights the power of citizen science. The discovery came from volunteers, people with no formal training in astronomy who donated their time to examine data. They found something professionals might have missed. Not because professionals aren't skilled, but because there's too much data and too few eyes. Crowdsourcing works. It democratizes discovery. It lets anyone with curiosity contribute to our understanding of the universe. And that's beautiful. The search continues. Automated algorithms now scan Kepler data and data from its successor, TESS, the Transiting Exoplanet Survey satellite. They're looking for more stars like Tabby's, more anomalies, more mysteries, and they're finding them. Each one is a puzzle, a chance to learn something new about how stars and planetary systems behave. Some will have simple explanations. Others will remain mysterious for years. That's okay. Mystery drives science. It motivates us to build better instruments, develop better theories, ask better questions. There's a philosophical angle, too. The Dyson swarm hypothesis assumed a certain kind of civilization, one that grows, expands, consumes. A civilization that needs ever-increasing amounts of energy and builds megastructures to get it. But maybe that's not inevitable. Maybe advanced civilizations find other paths: efficiency, sustainability, virtual realities that require less physical infrastructure. We assume aliens would think like us, value what we value, build what we would build. But they might be fundamentally different. Their technology might be invisible to us, unrecognizable. We might not even know what to look for. Tabby's star reminded us to keep looking, though, to stay curious, to remain open to possibilities. Because the universe is stranger than we imagine. Stars do unexpected things. Nature creates phenomena we haven't cataloged. And every now and then we stumble upon something that challenges our assumptions. That makes us wonder. That keeps us reaching for the stars, hoping to find something extraordinary. The dimming continues. Observers monitor Tabby's star regularly, waiting for the next event, the next clue. Maybe one day we'll have a complete explanation. A model that accounts for every dip, every variation, every quirk. Or maybe the star will keep its secrets a little longer. Either way, it's become a symbol, a reminder that the cosmos is full of wonders we're only beginning to understand, and that sometimes the most profound discoveries come not from answers, but from learning to ask better questions. All these signals, all these mysteries, they've led us across the universe and back. From the dawn of time to our nearest neighbors. From bursts that last milliseconds to patterns that unfold over centuries. And now, as we gather everything we've learned, it's time to ask what it all means. What these cosmic whispers tell us about the universe we inhabit and our place within it. We've traveled far tonight, from a 72-second whisper that appeared once and never again to bursts of energy that outshine galaxies. From microwave ovens masquerading as cosmic phenomena to the ancient light that carries memories from before stars existed. From signals near our closest neighbor that turned out to be echoes of ourselves to explosions so violent they could end civilizations. From a star that dims without reason to patterns in the oldest light that suggests the universe remembers something from before it was born. We've listened to the cosmos. And what have we heard? Mostly silence. Beautiful, mysterious, haunting silence. But here's the paradox. That silence is not empty. It's full of questions, full of possibilities, full of signals we haven't decoded yet or haven't detected at all. Every mystery we've explored tonight points to the same profound truth. The universe is speaking constantly in languages we're only beginning to learn. And the greatest mystery isn't any single signal. It's the absence of the one signal we've been searching for all along. The one that would tell us unambiguously, we are not alone. Enrico Fermi asked it in 1950 during a casual lunch conversation at Los Alamos National Laboratory. He was talking with colleagues about UFO reports, recent calculations about stellar formation, and the probability of intelligent life. And suddenly he asked, "Where is everybody?" His question was simple but profound. If the universe is so vast, if there are hundreds of billions of galaxies, each containing hundreds of billions of stars, if even a tiny fraction of those stars have planets capable of supporting life, where are all the aliens? Why haven't we seen them? Why haven't we heard from them? Why is the sky so quiet? This became known as the Fermi paradox, and it has haunted astronomers, physicists, and philosophers ever since. Because the math suggests we shouldn't be alone. The Drake equation, formulated by Frank Drake in 1961, attempts to estimate the number of active communicative civilizations in our galaxy. You multiply factors, the rate of star formation, the fraction of stars with planets, the number of planets that could support life, the fraction where life actually develops, the fraction where life becomes intelligent, the fraction that develops technology, and the average length of time such civilizations transmit detectable signals. Depending on the values you choose, the equation gives you anywhere from 0 to millions of civilizations. But we've found none. Not one confirmed signal, not one piece of unambiguous evidence, just silence. Why? The possible answers are numerous. Some are hopeful, some are terrifying. Maybe civilizations are common, but they don't last long. Maybe they destroy themselves through war, environmental collapse, or technological catastrophe before they can communicate across the stars. Maybe the great filter, the barrier that prevents life from becoming spacefaring and long-lived, is ahead of us, not behind. Maybe we're approaching it right now, or maybe the filter is behind us. Maybe intelligence is astonishingly rare. Maybe the jump from single-celled organisms to complex life is so improbable that Earth is a cosmic fluke. Maybe we're the only ones, the first, the only. Alone in a universe so vast, it makes the word lonely feel inadequate. Or maybe they're out there, but we're looking in the wrong way. Maybe radio is primitive, a brief technological phase that civilizations outgrow quickly. Maybe advanced societies use quantum communication, neutrino beams, or methods we can't conceive. Maybe they're here, but we don't recognize them. Maybe intelligence doesn't always look like us. Maybe it doesn't build radio telescopes or launch spacecraft. Maybe it exists in forms so alien we wouldn't know it if we saw it. Maybe consciousness itself is more diverse than we imagine. Or maybe they're hiding. The dark forest hypothesis, popularized by science fiction writer Liu Cixin, suggests that the universe is filled with civilizations, but they all stay silent out of fear, because advertising your presence might attract attention from hostile neighbors. Maybe the galaxy is a dangerous place. Maybe survival means silence. Maybe we're shouting into a forest where everyone else is hiding, and our broadcasts are a beacon that could bring doom. It's a chilling thought, one that makes you wonder if SETI, the search for extraterrestrial intelligence, is wise or reckless. Do you think we should keep listening, or should we stay quiet just in case? But let's consider another possibility, one that's less about them and more about us. Maybe we're not listening carefully enough. Maybe the signals are there, buried in noise, waiting for better instruments, better algorithms, better understanding. The wow signal appeared once. We never saw it again. But what if it's still out there broadcasting, and we've just been pointing our telescopes in the wrong direction? What if fast radio bursts, those millisecond flashes from across the universe, are beacons, lighthouse pulses, from civilizations far more advanced than ours, and we're only now beginning to catch them. What if the anomalies in the cosmic microwave background aren't natural fluctuations, but engineered patterns, messages written in the fabric of space-time itself, and we lack the sophistication to decode them? Every mystery we've discussed tonight teaches us humility. The wow signal taught us that a single event, no matter how compelling, is not enough. We need repetition, confirmation. The Periton phenomenon taught us to check our assumptions, to look for mundane explanations before invoking the extraordinary. BLC1 taught us that even when a signal passes every initial test, rigorous analysis can reveal terrestrial origins. Gamma-ray bursts taught us that the universe is capable of violence we barely comprehend. Tabby's star taught us that nature is strange enough without aliens. And the cosmic microwave background anomalies taught us that the universe might be more complex, more layered than our theories allow. But they also teach us hope, because every mystery solved opens new questions. Every signal detected expands our understanding. We've learned that the universe is dynamic, active, full of events and phenomena we never predicted. We've learned that space is not a silent void, but a cacophony of signals, most of which we're still learning to hear. We've learned that patience and rigor pay off, that science works, that the truth, however complex or disappointing, is always more valuable than comforting delusions. And we've learned that the search itself matters, the act of listening, of building better telescopes, of training our instruments and our minds to detect the faint whispers of the cosmos. Because even if we never find aliens, even if we are truly alone, the search teaches us about ourselves. It reminds us that we are part of something vast, that we are made of atoms forged in the hearts of dying stars, that we are the universe's way of knowing itself. And that's not nothing. That's extraordinary. Carl Sagan once said, "The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself." Every signal we detect, every mystery we ponder, is the universe reaching out to understand its own nature. And we are the instruments through which that understanding happens. We are the ears, the eyes, the minds. We are the part of the cosmos that woke up and started asking questions. Tonight we've explored some of the most enigmatic signals ever detected from the universe. 72 seconds of possibility, milliseconds of cosmic violence, microwaves from the kitchen, ancient light-carrying secrets from the dawn of time, a false alarm from our nearest neighbor, the brightest screams ever witnessed, a star that dims without explanation. Each one is a thread in the tapestry of our cosmic story. Each one adds texture depth, meaning to our understanding of reality. But the story is far from over. Right now, as you listen to these words, telescopes around the world are scanning the skies. SETI researchers are analyzing data. Citizen scientists are examining light curves. Satellites are detecting gamma rays, X-rays, radio waves from sources billions of light years away. The search continues, the listening goes on, and maybe one night a signal will appear, a signal that doesn't fade, that repeats, that shows unmistakable signs of intelligence, a signal that changes everything, that tells us we are not alone, that the silence was never silence at all, just a conversation we hadn't learned to hear yet. Or maybe we'll continue to find natural wonders, phenomena that challenge our understanding and force us to expand our theories. Maybe the universe will keep surprising us with its complexity, its beauty, its strangeness. Maybe the mysteries will never end. And maybe that's okay. Maybe the not knowing is what drives us, what keeps us curious, what makes us human. I want you to think about something. Every signal we've discussed tonight, every mystery represents a moment when someone looked at data and saw something that didn't fit, something unexpected. And instead of ignoring it, instead of dismissing it, they investigated, they asked questions, they published their findings, they invited scrutiny. That's the scientific method, not a set of beliefs, but a process a way of finding truth through evidence, through testing, through the willingness to be wrong and the courage to correct mistakes. The universe doesn't care about our beliefs. It doesn't conform to our wishes. It simply is. And our job as curious beings with the capacity to wonder is to observe it as accurately as we can, to measure it, to model it, to understand it. And when we find something we can't explain, to resist the urge to fill the gap with easy answers, to sit with the uncertainty, to keep looking, to keep questioning, because that's how we learn, that's how we grow, that's how we become worthy of the cosmos that created us. The signals we've explored are more than data points. They're invitations. Invitations to think bigger, to imagine more, to push the boundaries of what we know. They remind us that reality is richer than our everyday experience suggests, that beyond the mundane world of bills and traffic and daily routines, there's a universe of unimaginable scale and beauty, a universe that speaks in bursts of gamma rays and radio waves, a universe that dimmed when we weren't yet born and will continue long after we're gone, a universe that doesn't need us but through some cosmic accident gave rise to us anyway. And we in turn have chosen to listen, to point our instruments skyward, to ask, what's out there? Not because we expect easy answers, but because the question itself is worth asking. Because curiosity is what makes us human. Because the search for meaning, for connection, for understanding is the most profound thing we do. So, where does this leave us with questions mostly? With wonder, with the knowledge that we've barely begun to understand the cosmos, with the hope that one day, maybe soon, maybe in 100 years, maybe never, we'll detect a signal that changes everything. Or with the acceptance that we might always be alone, the universe's only witnesses to its own majesty. Either way, we listen, we search, we wonder, because that's what we do. That's who we are. Creatures of stardust and curiosity standing on a small planet, orbiting an ordinary star, reaching out into the vastness, hoping to hear something echo back. The universe has whispered to us tonight, in signals brief and bright, in mysteries unsolved, in patterns we don't yet understand. And though the answers remain elusive, the questions themselves are gifts. They remind us that there's always more to learn, always more to discover, always more to wonder about. Thank you for drifting with me through these cosmic mysteries, for staying curious, for letting the wonder in. The universe is vast and we are small, but in our smallness, we've learned to listen to the stars, and that makes us in a very real way magnificent. Perhaps one night as you look up at the sky, you'll remember these stories, the signals that came and went, the mysteries that remain, and you'll feel it. That connection to something larger, that sense of being part of an ancient ongoing conversation between matter and energy, between chaos and order, between silence and sound. The universe is speaking, and we are learning slowly, patiently, beautifully to understand. Sleep well. Dream of distant stars. Dream of signals yet unheard. Dream of the day we might finally answer. That oldest question, are we alone? And know that whether the answer is yes or no, the cosmos is still beautiful, still mysterious, still worth exploring. Until we meet again beneath these quiet skies, rest easy. The universe will keep its vigil, and so will we. Good night,